All right, so now we're going to talk about step size control. And the basic idea behind this is that, as we know, it's like when you look at the error term for, say, a Runge-Kutta method, right? The error involves some derivative of the function, it's like which you don't necessarily know, and then the time step, some power at the time step, with some sort of constant in front of this. So the basic idea, if you will, is that it's oftentimes the case that you would like to exert control over the local error you make for every time step. The way you do this is that you adjust the step size, it's like so that that error is below some user-provided threshold. Okay, and the problem, of course, is that you have to estimate it's like these it's like analytical derivatives, and so that's what we're going to discuss right now. So computing the local error for a Runge-Kutta method sort of requires computing sort of analytically computing derivatives of the exact solution, which of course it's like involves it's like implicitly differentiating the differential equation. So this leads to the idea of approximating this, right? Instead of trying to actually analytically compute, it's like these derivatives. Okay. So let me sort of just sketch sort of intuitively, it's like how one might go about doing this. So let's suppose the following. So let's suppose that we have two methods. So we have two different methods which give sort of approximations. Let's say Zyn, right, of order P, and Zn of order 1 higher, say P plus 1. So what I mean by that is that Yn is equal to y at Tn plus some Ch to the P plus 1. So this is the order P method because its local truncation error is order P, sort of big O of P plus 1. And then we have a big O of H to the P plus 2. And then we have a Zn, which is one order higher. So Yn plus big O of H to the P plus 2. Okay. So what we can do, obviously, is we can compare it's like these two solutions. So we can subtract one from the other, and you get Ch to the P plus 1 is sort of Yn minus Zn plus something which is big O of H to the P plus 2. All right, and as is often the case, it's like we'll assume that this is small enough that we can ignore it, and so we'll say that Ch to the P plus 1 is related to this Yn minus Cn. Okay. So we estimate ch to the p plus 1 by yn minus cn. Okay, so and then we choose h, right, so that the local error, right, or the leading error term, sort of leading local error, right, is bounded from above by some tolerance epsilon. Okay. 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 So we have that yn minus cn, say the old value, right, divided by h to the p plus 1, again the old value, right, is approximately equal to this constant c, right, which is again approximately equal to yn minus zn, some new value, divided by h p plus 1 mu. Okay, and we want this to be less than some safety factor times this tolerance epsilon divided by h mu to the p plus 1, right? And that's because we want c times h to the p plus 1 nu, it's like to be less than the safety factor times epsilon, right? Because c h to the p plus 1 is the leading truncation error term for the yn estimate. Okay? All right. So where nu is a safety factor, say 50%. Okay, which allows us to tune. It's like this this thing here. Okay, so anyway, so now, right, with this in mind, it's like we can figure out what we need, right? So we want h nu, right, to be less than h old times nu epsilon over yn minus cn old to the 1 over p plus first power. Okay, and the point is that satisfying this inequality, right, right, so how do you do this? What you basically do is that you have this is less than this, right? So maybe let me just try to work that out, right? You have yn minus cn old divided by h to the p plus 1 old is less than nu epsilon over h nu p plus 1. Right, so this gives me h nu p plus 1 is less than h old p plus 1 multiplied into this. All right, and then taking the p plus first root gives me h nu is less than h old and then this quotient, it's like to 1 over p plus 1. Okay, yeah, so that's where we got this inequality from. It's just saying this, which is approximately c, which is approximately this, and this is the thing we care about, right, is less than this thing, and so we just have this expression in terms of the old values. It's like be less than this thing, which involves the new time step. Okay, and so we have to have something which satisfies an inequality like this. All right. Okay. So. And the basic idea then is that actually you want it not just to be less than, but you sort of want it to be about roughly comparable, right? So if the time step is too small, for example, it's like you might want it to be, it's like you might want to increase it if it's so that it's roughly comparable to this thing on the right-hand side. Okay. All right. So the point is that when the error becomes significantly smaller, then nu epsilon, right, then we can increase the time step instead, increase the step size. All right. So now, now what we'd like to do then is to ask how can you efficiently compute, it's like this matched pair of methods. It's like which differ in the order of accuracy by just one. Okay, and so this leads to a class of Runge-Kutta methods. It's like which we'll talk about in a little bit. But let me just stop here for now. And we'll talk about these sort of methods which sort of are well adapted, it's like to this problem of adaptivity.